Hey guys, welcome back. So, one of the other things I want to talk about is we want to be able to see, is there a temperature at which the spontaneity of this is going to change? So, if it's spontaneous only at some temperatures, where is that going to change? Where is it going to be? So, above that temperature, it's spontaneous, or below that temperature, it's spontaneous. If it's not spontaneous all the time. And we have some reactions that are always spontaneous. And that's when our delta H is negative and our delta S is positive. Then our delta G is always negative, and therefore it's always spontaneous. If my delta H is positive, my delta S is negative, then my delta G is always positive, and therefore that is never spontaneous as written. We have to flip it to get it to be spontaneous. But we do have cases where I have positive on delta H and positive on delta S, or negative on delta H and negative on delta S. And whether or not it's spontaneous has to do with what the temperature is. So we have to find a temperature where it is favorable for that reaction to occur from an entropy point of view to drive those reactions. Okay? And we can guesstimate, or actually calculate, the temperature at which that will occur. So when a reaction is no longer favorable, or we're changing favorability from unfavorable to favorable, it goes through delta G equals 0. The sign of delta G changes from positive to negative, or negative to positive. And so delta G equals delta H minus T delta S, and delta G is 0. So then delta H is equal to T delta S. That can be further rearranged so that we have delta H over delta S, which will tell us the temperature at which that will change. Okay, so we want to be able to solve for that T. So we're going to do some examples of solving for that T to see where this happens, to see where it becomes spontaneous or non-spontaneous, and talk about how that temperature change affects that. Is it going to be spontaneous above that or below that? Okay, so we can do this for many of the same things that we talked about before. Now remember, we talked about this reaction right here. And we talked about this reaction right here. So I want to look and see what those values were that we calculated before. Now, we calculated back here that delta H for under standard conditions, my delta H was negative 146.73288. Okay. Negative, let me just copy it. I don't have to remember. And of course, these are the standard formation ones that we calculated previously. So let's go get the delta S for that particular reaction again. So we calculated the delta S for that reaction as well, and that was this value right here. We'll paste that right there. Doesn't fit very well. And I just want to verify the sign on that. So I thought it was negative. It is. I didn't catch the negative. Go, awesome. See, this is what I mean about checking our signs. So, since it didn't fit very well, negative 294.05144 joules per mole, and this is kilojoules per mole. So those are the two values for that one. Now, when we talk about the other one that we did previously, go back and get some values for that. And those were up here. So my delta S for this first reaction was this. And then I want to go back and get my delta H. I think is that there. Yeah, delta H is right here. Why on earth did you do that? Okay. Sometimes it misses weird parts of it, and I don't understand why it does that, but okay, fine. So that's my delta H value for that one. And again, that's delta H not F. So I have a delta S and I have a delta H for both of these. So I should be able to use this equation that we have right here, this one right here, that delta H naught over delta S naught. And that will give me that temperature, which that will change. Okay. So let's take a look at this. Now, since my delta H here is negative and my delta S is also negative, I would expect that that's not always going to be favorable. So we should be able to find the temperature at which that changes. Okay. So if I do that, I take that negative 673.2056, and remember that's kilojoules. And we divide that by, and negative, hold on, sorry, I just want to check my units. Joules? Okay, it is joules. Just want to make sure we were in joules and not kilojoules. So I want to do a conversion on that one before I do that. So I'm going to take my negative 92.31996 and divide that by 1,000. And that gives me negative 0.0923196 kilojoules per Kelvin. So negative 0.0923196 kilojoules per Kelvin. Now notice if I do that, and we look at the units that we have right here, our kilojoules will cancel, and that Kelvin will come up to the top, and so that will give me a temperature in Kelvin, which I can work with. So I take my negative 673.2056. I divide it by this answer that I have from before. And then that gives me the temperature. .7292, and I'm going to leave it as 4 digits, Kelvin. Now, looking at the signs, I see that delta H is negative and delta S is negative. So below this temperature, the delta H is a bigger contributor, and so any temperature below this should be spontaneous. Any temperature above this would not be spontaneous. Okay? So that's what we're going to be doing there. Now, I want to look at this one. And of course, we need that delta H naught over delta S naught. And of course, I want to calculate my delta S in terms of kilojoules. So I'm going to take the negative 294.05144 and divide that by 1,000. And then I'm going to take the negative 146.73288, divide it by that number. So delta H naught over delta S naught is negative 146.73288 over negative 0.294051444 kilojoules per Kelvin. And that's going to equal, and notice those are both negative, so that's going to be 499 Kelvin. Okay, awesome. So what does that tell me? Well, okay, that tells me that at any temperature below that, that delta H will be a big enough factor, because it's negative, but not very big, that we will be able to keep this spontaneous, okay? What I am concerned about is not that you can tell me whether it's spontaneous above or below, although you should be able to figure that out. But what I'm concerned about is, can you identify the temperature at which that sign changes? So setting it equal to 0, solving for it in this way, can you do that? And let me verify something while we're sitting here. Yeah, I didn't think so. So that equation is not on your test. So I'm expecting that you know that when it stops being spontaneous, delta G is 0. Okay, because that's where we lose our spontaneity. Okay, so that's how we do our temperature dependence. Questions, comments, problems? I hope not. Let us continue to talk a little bit, and let's talk about phase transitions and free energy. So because the temperature is constant during a phase change, the free energy is 0 because the system is at equilibrium. Okay, so we're trying to get everything over this hump while we're doing that. There's a large change in spontaneity in these processes, however. So you go from more ordered to less ordered. It's a negative entropy. It's less ordered, and thus is favorable. Okay, so when we go from solid to liquid, that's a good thing. My entropy goes up, so my disorder goes up. We can measure the molar heat of the change using delta S equals delta H over T. So I'm not going to ask you to calculate that, but that is how we can do it. So that will give you some idea of what we're talking about in terms of how much entropy we get from that. Okay, so you go from less ordered to more ordered, it's positive. We go the other direction. They'll be equal in size but opposite in sign. Okay. Now I did ask you to do some practice with this one, but I can guarantee you I'm not going to ask you that on the exam. So if you choose to do it, great. I will put answers on D12 for you. It's just so you can see how those are worked. But that is not something that I'm going to expect you to do on the test. Okay? Questions, comments, problems about that? I hope not. But if there are, you know how to get a hold of me. At least I hope you do at this point. Email, phone, WebEx, whatever. Let me know what's going on. Okay? And we have one last topic. I'm going to stop here